Welcome to my first video lab report. My name is Michaela Bartram, and today we will be exploring constant velocity. We will be observing constant velocity of a pen, particularly my pen, and hopefully our results will be that the net force is 0. That's my initial assumption, and I'm going to prove that the net force was 0 on my pen. Here we go. This is the tracker software, which is what I uploaded my video to. I recorded it with my cell phone and then turned it into an MP4 and put it on here. You can see the tip of my pen has a blue measuring mark on it that shows that the tip of my pen is 0.013 meters, which is used to scale the rest of the video. And then you can also see the little red dots on my thumb. Those show how my thumb travels throughout the entire video in contact with the pen. That's just the point that I chose to keep track of throughout the entire video. Also, the orientation is something to keep in mind. The negative x direction, or what would normally be a negative x direction, is actually the positive x direction, and the same goes for y. Positive y is actually negative y in this case, but y doesn't really matter because we're only looking at the direction, x direction, because it's only moving in the x direction. Alright, so this is me playing the video. That was it. It was great. You can see in the top right corner where the points go, and that's a positive slope showing, and it's also a relatively straight line with a little bit of deviation, but the best fit line would be straight and there is no curve to it, so that doesn't show any change in acceleration, which is great. In order to model the pen's movement on VPython, we have to derive the velocity from the fundamental momentum principle, which is momentum equals gamma times mass times velocity. In this case, gamma is about 1, so we don't have to worry about it. And then we can also see that the change in momentum is equal to mass times the change in velocity, which is also equal to the net forces times the change in time. So if we rewrite that as the final momentum minus the initial momentum equals the net forces times delta t. And then if we subtract the initial momentum from both sides, we get the final momentum equals initial momentum plus F net delta t. And since momentum equals mass times velocity, if we divide by the mass, then we just get the velocity. So final velocity equals initial velocity plus the net forces divided by the mass multiplied by the change in time. In order to model the movement of the pen on VPython, we have to calculate some of our variables first. First, we have mass, which is 21 grams, and then we need the ball velocity, which is change in distance over change in time. For the change in distance, I took the last x value that I found in the tracker software and took from that the initial x value, which was the initial position, which you see underneath that. And then the change in time, I took the initial time, which is 0, and I subtracted it from the final time, which is 1.066 seconds. So the change in time per frame is 0.033 seconds, which is important. And then using all that, we get the velocity to be 3.62 times 10 to the negative 2 meters per second. Here we took the mass of the ball and we plugged that in. We took the initial position, which I got from right here, and we plugged that in also. The z is 0 because we're only looking at x and y. We only have x and y axes. The ball velocity, it's only moving in the x direction, is 0.0362. I made it negative so that when we actually model the ball rolling, it will be going in the negative direction. But then if you scroll down here, you can see that when I graphed it, I took the negative of the position so that my graph will be positive. This accounts for the fact that my negative x direction on my tracker is actually the positive x direction since I moved the axes. Also, initial time is 0, delta t is 0.033, which we get from over here. And then while t is less than the final time, I just plug in all of that. My vector for force is 0, and I plug it into the velocity formula that I derived over here. To VPython, it's time to run our program. So we're going to go to run module, and it's going to take a second, and then we will see our ball moving to the left, which it does in the video on Tracker, and our graph going in the positive direction with a positive slope, and it is linear, which is good. In VPython, I added a line that said to export the data from the model that I made in VPython into a CSV file. And I opened that in Excel and I graphed it, and that's this red line right here. And I also copy and pasted the cells from Tracker with the distance versus time numbers, and I plotted them right here. You can see that the red and the blue are going in the same direction, have relatively the same slope. The blue is a little bit non-linear, but that's just experimental error. And we have distance in meters versus time in seconds. Now, let us consider what if there was a net force acting on the pen. Well, what would happen if there was a net force acting on the pen using VPython? So right here we have our Fnet, and it's vector 0, 0, 0, because in our model there was no net force. But let's just say that we added a net force in the x direction, because that's the only direction that the pen was moving. I'm going to make this -5 just because the negative x direction is actually the positive x direction in the Tracker software. So I'm going to take this and I'm going to run it and see what happens. We can see that with a net force of 5 going in the x direction, there's a parabola moving in the positive x direction. We no longer have linear data points. This is because there is no longer constant velocity. The velocity is accelerating at a constant acceleration, which is the constant net force of 5 that's being applied to it. And since there's net force, we are no longer linear, which is very important because our data is linear from the Tracker and from our initial model with a net force of 0. What does this mean? This means for my pen there is no net force and velocity is constant because the graph of the distance versus time points for the pen was a linear graph in the positive x and y direction, and when there was 0 net force on the VPython model, it was a linear graph in the positive x and y direction. If there was any force, it would be a parabola as previously shown. This proves my initial assumption that the net force is 0.